Welcome to IB Chemistry exam preparation, exam tips for both standard level and higher level. I'm going now to continue in our lesson for today in topic 11.1. Through our lesson, I'm going to focus on different types of errors. We're going also to discuss how can we improve, how can we reduce and eliminate these errors if presented. We're going also to go through calculating the percentage error as well. So let's start. We have three main types of errors presented inside the lab mainly. The first type of error is the parallax error. The second type of error is classified as being random errors. And finally, we have number 3, which is the systematic errors. We will start firstly with the parallax error. Whenever you want to read a graduated cylinder, a pipette, a thermometer, you need to have your eyes parallel to the scale as described in position number 2. So inside this figure, I have a certain volume of water presented inside the graduated cylinder. Whenever you want to read, your eyes should be parallel to the scale, so your reading will be 19.7 milliliter or cubic centimeter. On the other side, if your eyes were above the scale, so the number that will be taken is below the actual, which is 19.62. But if it is below the scale, the number it will be above, which is 19.82 milliliter. Usually, the parallax error is classified under random error since it doesn't have one direction unless you know exactly the position of your eyes. So for each trial, if you know exactly your eyes are above or below, so we can classify the parallax error as being systematic. We're going now to start with random errors. Starting with random errors, we need to know, number 1, these types of error arise from the use of different equipment and tools. And since each experimental lab is with a specific tool and equipment to be used, so random errors is presented always. And we actually cannot remove it. We can only eliminate or reduce. Number 2, random errors can lead to readings being above or below the true value. So we don't have a specific direction. They could be above or could be below. If you refer back to my previous lesson, which is part 1 from section 11.1, we discussed the meaning of the plus minus and the absolute uncertainty which is presented from the use of different equipment. Number 3, random errors arise from the imprecision of measurements. So it will affect how precise the values are compared with each trial. So inside this example, I have here the plus minus, which is the absolute uncertainty taken from the balance. So in this situation, I have a random error inside my mass of a piece of wood. Since I'm not certain whether it is 8.32 exactly, it could be between the 8.32 and it is a plus minus 0.01 gram. So what does this mean as a random error? Inexact number presented, it's my last decimal. So I have here the uncertainty presented from my tool. So if I'm going to subtract 1, so it will be 8.31. And if I'm going to add another 1 to this inexact, it will be 8.33. In this situation, my mass, it is any number which is between 8.31 and 8.33. This type of error, it is classified as being random errors. For random errors, they cause to have small errors are more probable than large errors, and the negative deviations are as likely as positive. The actual value may be either greater or smaller than the value you record inside the lab. So based on the random error, it will cause to have small errors. So we will not have a very large deviation compared with the actual. Since the plus minus or the absolute uncertainty taken from the tools and different equipment, they are actually small numbers. They have only few decimal places to be counted into the measurement numbers given. Now the point is how to reduce random errors. Random errors can be not removed at all. You cannot completely remove them. You are using equipment, you are using tools, so they are presented always. So you cannot remove, you can only reduce, but it can be reduced or minimized. To reduce random errors, you can do the following. Number one, you need to take more reading trials and to calculate the average. Number two, random errors can be reduced with the use of more precise measuring equipment. So inside the past paper, as a multiple choice or inside your internal assessment lab report, if you want to reduce or to minimize random errors, you need to go through more trials and taking the average and the use of more precise equipment. The meaning of more precise equipment. To understand the more precise equipment, I need to refer to this figure. Inside this figure, I have 3 different tools can be used in order to measure the temperature of a solution. So I can use a normal thermometer, I can use a digital one, and I have number 3, another digital. The difference between one and another is in the number of decimal places which are presented. Besides that, it is the plus minus uncertainty of the tool that I have. Considering which one is more precise. Of course, the third one is considered more precise. So if you have the opportunity to use one of these inside the lab, you need to pick the one which is more precise, since it will reduce, it will minimize the random errors, and the data that will be obtained, it will be more and more precise. So if you have more decimal places given by the plus minus uncertainty reading, so this is considered as being more precise equipment, and this will eliminate your random error. Another example here is the use of two different balances. I have balance number 1 and I have the second one. Which one is considered more precise? Definitely the first one is more precise, since the plus minus is 0.001 gram, while the second is plus minus 0.01 gram. So this one is more precise, and this one is less precise. Another time, if you have more decimal places presented, this will give you more precise data and less random errors. Continuing now with systematic error. The first point, systematic errors arise from a problem in the experimental setup or inside the method. Number 2, systematic errors results in the measured values always deviating from the true value in the same direction. So each time you are doing the error, you will have one direction for the error. It will be either higher or lower than the actual value. For example, if you are inside the lab, you want to measure the mass of a precipitate. So definitely you're going to filter out the precipitate. After that, you will take the precipitate and you will put it inside the oven in order to dry it. So if the method says that it dry it inside the oven for 2 minutes, and these 2 minutes, they are not enough in order to fully dry. So what will happen? You're going to have the mass as being larger than actual. Repeat the experiment another time. You are using the same method, so you will also heat inside the oven for 2 minutes. So another time the mass will be higher than actual since it is wet. So this type of error, which comes from the method or from the experimental setup itself, it is affecting in one direction. So I can know in which direction. And in this situation, if I overcome the problem, I can remove this error and eliminate it at all, not only to reduce it. Systematic errors affect the accuracy actually. So it affects how close is your result to the actual data, and systematic error may cause to have large deviation from the actual, not as the random, that always causes to have only small error presented. Systematic error can arise from a defect in the instrument. When talking about a defect in the instrument, so perhaps there will be incorrect calibration of the instrument or tool. Remember that all tools or equipment used inside the lab should be calibrated before using. I'm talking about balance, I'm talking about pH meter, spectrophotometer, etc. So before being used, they are checked to be calibrated. So if there is any defect in this instrument as being incorrectly calibrated, this is considered systematic error. Remember this point for the multiple choices. Errors in the way the measurement was taken, and experimental methodology error. Continuing now with some examples for systematic errors. Errors due to partial loss of substance weighed and transferred. Errors in measurements of mass due to incorrectly calibrated balance. Incomplete dissolving of a substance. Of course, this will cause to have incomplete reaction, so this will affect your result in one direction. Incomplete reaction between the reactants. Heat exchange to the surrounding. This is so important for the energy chapter. This is considered as heat loss to the surrounding, which is a very important systematic error for energetic chapter. Having traces of liquid in the pipette or graduated cylinder. Incomplete drying of a sample. I can consider also another systematic error while doing up the titration. Perhaps it's the detection of the endpoint of the titration as being inaccurate. Maybe you will exceed the endpoint by adding more titrant, so this is also considered as another systematic error. How can now we reduce systematic error, or even we can eliminate and remove it at all from the experiment? Number one, errors are consistent and they are easier to fix. So if you know them, you can easily fix them. If there is a problem in the instrument itself, so calibrate it. If there is a problem in the method in one step, so you need to rewrite your method and to enhance it another time. Number two, better attention to experiment design. So it is a better attention for your method, for your steps while writing it inside your lab report. And number three, of course, it is calibrating and fixing up the instrument. Now, we're going to have what is the meaning of percentage error, which is also so important when deciding the type of error represented inside any lab or any internal assessment. We're going to go through the rule of calculating the percentage error. The percentage error rule is the actual value minus experimental value over actual times 100%. What's the meaning of the actual? Actual, it is the literature value, which is the correct value based on the reliable reference that you have. So for example, if you are measuring the boiling point of water, your actual value, it will be 100 degrees. The experimental value, it's the average value that you have obtained, and usually it is an average since you do the experiment for more than one trial. So the value here is obtained as an average. So if you apply on the experiment and you determined the boiling point of water for more than one trial and your average was, for example, 98 as a degree, and you want to go through the calculating part of the percentage error, so you will apply on your rule. So the percentage error in this situation, you will take the absolute value since it is always positive, not negative. The actual value is 100. You're going to subtract minus 98 as experimental over 100 times the 100%. So this is how you calculate the percentage error for any experimental data. You cannot calculate the percentage error if you don't have the actual and you don't have the experimental. Of course, the actual, it is from the literature, taken from table, taken from the internet, taken from different resources. Whenever the value of the experimental value is so close to the literature value, this of course will give you a smaller percentage error, indicating that the errors presented inside your experiment is small. A very important note, I have it in the second point right here. If the percentage error was higher than percentage uncertainty, so I have now the percentage error after being calculated, it was higher than the percentage uncertainty of the value. When talking about the percentage uncertainty, you need to refer back to the first part of video, which is about measurement and uncertainty, into which I discussed in details how can you determine the percentage uncertainty for any calculated value. So inside your lab report, you need to calculate the percentage error, you need to calculate the percentage uncertainty, taking into consideration all the variables presented inside the law and their total percentages uncertainty based on the absolute uncertainty taken. You can refer back to the video, which is section number 1 or part number 1. Now, if the percentage error is larger than the percentage uncertainty, what does this mean? This indicates that systematic and random errors, they are both presented. So you need to refer inside your internal assessment that this lab contains both systematic and random. Then you're going to specify what are the systematic and the random error presented. But the second situation, if your percentage error was smaller than the percentage uncertainty, in this situation, this is an indication that your experiment mainly contains only random errors. And this is also another indication that the problem is presented due to the tools and the equipment that you have used. So if you want to reduce it as possible, you need to use more precise tools and to repeat the experiment for more than one trial. On the other hand, your method, it is perfect and there is no error inside it. This is definitely not the case in most lab reports. Usually the percentage error is higher than the percentage uncertainty. Inside energetic chapter, whenever we want to calculate the enthalpy change of any chemical reaction, the percentage error is presented so high due to the heat loss to the surrounding, and in some cases it may reach 40 and 50%. I'm done with my lesson for today. So you need to be familiar on calculating the percentage error and to know the different types of errors and how can we reduce. In my second lesson, we're going only to practice on some past papers into which section 11.1 questions taken from both paper 1 and paper 2 will be answered. Thank you for watching.